Alright, so let's look at how the elimination process happens when we're dealing with an equation that has more variables than, or a system that has more variables than equations, right? The ones that we're used to dealing with and that we introduce systems of equations most often have the same number of variables as equations, right? And we in fact know that in order for a system to have a single solution, it has to have at least as many equations as variables. So in this case we have 5 variables, right? If I had any hope of this system having a single solution, I would need 5 equations. So what that tells me is I'm not going to run into the single solution case. So I don't know if it's going to be 0 solutions or an infinite number of solutions. Remember, those are the only things that can happen: 0, 1, or an infinite number of solutions. But we'll go through and we'll find out through the elimination process. All right. So let's throw this thing into a matrix, right? Into its augmented matrix, and make sure we copy everything down correctly. My lectures would be half as long if I would not fall for that trap every time. Okay, so here we go. So this is what, a 3 by 6 matrix? And so the process of Gaussian elimination starts this way. It says find the first column that has a non-zero entry. All right, so obviously this column has a non-zero entry. It has 3 non-zero entries. And then it suggests that you swap the rows if necessary. All right, so that the first entry in the top row is 1. All right, you want it certainly to be non-zero, but if you can make it to be 1, then you're even better. All right, once you've done that, you get to go through the process of eliminating, and we're always going to do this. We're always going to eliminate here, here, and then here, right? Those are our targets, right? So you start with your first non-zero entry and you want to eliminate the things before it, and then we'll see where to go from there. All right, we'll start from the first non-zero entry, eliminate the things below it. All right, so to do that, we're going to need to take -2 times row 1, add that to row 2, and replace row 2. So -2 times row 1, -2, 4, -6, -4, -2, -20. Row 2 is a 2, -4, 8, 3, 10, 7. And so when we add those, our new row 2 is going to look like this. And so we can put that in right here. Try to get a little more compact here. New row 2 looks like this. Row 3 is unchanged at this point. Okay, so we've got the 0 right there where we want it. Now we want to get rid of this one. Okay, so to do that, we're going to go -3 times row 1, add that to row 3, replace row 3. So -3 times row 1 is -3, 6, -9, -6, -3, -30. Row 3 is 3, -6, 10, 6, 5, 27. And then when we add those, we get a 0, 0, 1, 0, 2, -3. And that becomes our new row 3 in this new equivalent matrix. So we're going to go 1, -2, 3, 2, 1, 10. Row 2 is 0, 0, 2, -1, 8, -13. And row 3 is this 0, 0, 1, 0, 2, -3. Okay, so mission accomplished. We got the two zeros, the two terms eliminated above that first non-zero entry. Remember, we need that for to be an echelon matrix form. Okay. So once you do that, you then move over. You move down and over until you find the next non-zero entry. You have to move down. So we have to go down. We're done with this row. We now go down to this row and we find the first non-zero entry, and there it is. Okay, so now we want to eliminate everything below that. So to do that, we're going to need to take row 2 as is, but we'll add to that -2 times row 3, and we will replace row 3. Okay. So row 2 is 0, 0, 2, -1, 8, -13. -2 times row 3 is 0, 0, -2, 0, -4, and 6. And so we get 0, 0, 0, -1, 4, and -7 as our new row 3. So 1, -2, 3, 2, 1, 10. 0, 0, 2, -1, 8, -13. And then new row 3, 0, 0, 0, that's the 0 we wanted, -1, 4, and -7. So we've cleaned out the zeros, from that leading term. We've cleaned out the leading element. We've cleaned out the zeros below that leading element. And so now we move down and we find the next non-zero, and there it is. And of course there's nothing below it to clean out. Okay. And so this matrix is in echelon form, right? We have this stair step where the leading entries are all below and to the right of the previous leading entries. Okay, so let's see, that was a 7. Okay, now here's what's going to happen. When you go to solve this, the entries that have leading elements in them. So this would be the, let's see, this is the x sub 1 column, this is the x sub 2 column, x sub 3 column, x sub 4 column, and x sub 5 column. The entries that have leading terms, so there's a leading term in the x sub 1 column, there's a leading term in the x sub 3 column, and there is a leading term in the x sub 4 column. Okay. There you go. The terms that don't have leading terms in them, so that would be x sub 2 has no leading term and neither does x sub 5. Those are called free variables. Okay, free variables. So this is what happens if you ever put your matrix in echelon form, and if you have any free variables, then here's what you know. You get to, number one, you know that this system has an infinite number of solutions. Okay, an infinite number of solutions. And so what we're going to need to do is come up with a formula for the solutions. So the first thing we do is we identify the free variables, x sub 2, right, and x sub 5. All right, those are our two free variables. So what that means is these are the two variables you get to assign parameters to. So x sub 2 we'll call s, and x sub 5 we'll call t. Now we've done this before when we had an infinite number of solutions. We assigned a parameter to one of the variables. But now we have two free variables, so we each of them get a parameter. That means they get to be anything they want. And then now we're going to use back substitution to figure out what everything else needs to be, right? So if we start with this equation right here, this equation, let's just write it here, is minus x sub 4 plus 4x sub 5 equals -7. And if I make my substitution of t for x sub 5, right, knowing that x sub 5 is t, then that leads to x sub 4 equaling, right, x sub 4 equals 4t plus 7, right? So if you solve for x sub 4, you get it in terms of t. And so that's going to be the formula for x sub 4. We've got x sub 2 is s, x sub 5 is that, x sub 4 is that. To find the others, you're going to just move up. So let's go to that one. Let's put it in blue. And that equation is 2x sub 3 minus x sub 4 plus 8x sub 5 equals negative 13. Well, we know what x sub 4 is. It is 4t plus 7. And we know what x sub 5 is. It is just t. So if I can solve that equation for x sub 3, then I will know what x sub 3 has got to be. So just doing a little algebra here. So I'm going to have 2x sub 3 equals, let's see, that's negative 4t when I move it across, and add the 7 is negative 6. Add the 7 is negative 6, so x sub 3 is negative 2t minus 3. Okay, so there's the formula for x sub 3. And now if I want to find the last thing is x sub 1. I haven't used this equation yet, so let's use that here, right here. So that equation is x sub 1 minus 2x sub 2 plus 3x sub 3 plus 2x sub 4 plus x sub 5 equals 10. Right, let's make sure we got that right. We need some more room here. Minus 2x sub 2 plus 3x sub 3 plus 2x sub 4 plus x sub 5 equals 10. Now we can plug in what we know, right? X sub 2 is s. X sub 3, 3 times x sub 3 is minus 2t minus 3. X sub 4 is 4t plus 7 plus x sub 5 is t equals 10, right? It's kind of long. So x sub 1 minus 2s plus 2t, no, that's plus 3t, plus 5 equals 10. So that's going to tell us x sub 1 is going to equal 2s minus 3t and then plus 5, and there's the formula for that. So our solution, if we sometimes you'll just write it like this: x sub 1 equals 2s minus 3t plus 5. X sub 2 equals s. X sub 3 equals negative 2t minus 3. X sub 4 equals 4t plus 7. And x sub 5 equals t. We don't often write it in a an ordered pair or an ordered quintuplet right here. I guess that's what that would be. But remember, what this means is s and t, we are free to choose them to be whatever we want. And so when we do that, then that determines what everything else has to be. And so we have a formula that gives us the infinite number of solutions here.